Hello, in this video we are going to talk about first one-sided limits, and then we are going to also talk about calculating limits using the limit laws. But first, one-sided limits, we actually have talked about these things in the previous video. So we look at the output values of f when x, the inputs, get close to some number a. So f may or may not be defined at a, and we don't care when we look at limits. So we don't care about whether the function is defined or not. We just care about what happens to the values of the inputs which are getting very close to a. Okay, so the outputs of the inputs under f, which are close to a. That's what limit is. It's not about what happens at a. It's about what happens to the outputs of f around a. Okay, so after saying this, we have, of course, left-hand limits and right-hand limits. So we can look at limit from the left of a and from the right of a. So the left-hand limit, we write limit x goes to a from the left, that superscript minus, which I circled in green, means left-hand limit of f is equal to L, and then we say the left-hand limit of f is L as x approaches to a from the left. Here x is sufficiently close to a, and also it's less than a, okay? So as an example, let's say we have some function like the green graph here, the red graph here. So if we are approaching to 2 from the left of 2, or the inputs are slightly less than 2, but very close to 2, then look at the green output values. They are getting closer and closer to 5. So in this case, we say the limit of f as x goes to 2 from the left is equal to 5. Or you can also say the left-hand limit of f as x goes to 2 is equal to 5. You can say either way. And then similarly, we can also look at the right-hand limits. But in this case, we write superscript plus on top of a, which I labeled in red. So that means where x is approaching to a from the right of a with little bit larger numbers than a, but very close to a. Then the limit is equal to L, and then we say the right-hand limit of f is L as x approaches to a from the right. Again, similarly, x is sufficiently very close to a, and it's greater than a. And in the above example, the right-hand limit of f when x goes to 2 is minus 1. So let's look at the graph again. So when we approach to 2 from the right, as you see, the limit, the output values are approaching to minus 1. So the right-hand limit of this function as x goes to 2 is minus 1. Okay? So in general, if the left hand and the right hand limits are equal to the same number, then we say the limit exists. So let's say we have some function, let's say y, x, and let's say we have some graph like this. When x goes to a, from the left and from the right, the outputs are getting close to L. Then we say that the limit is L. Okay. So there are some important examples about one-sided limits. One of them is the heavy side step function. So this is actually turning the lights on, or in the circuit theory, switching a circuit on. So it has a graph like this. So it goes 0 until we hit 0, x equals 0 value, and then it becomes 1, and then it goes 1. So think about turning the lights on or switching a circuit on. First, it is 0. And then when we switch the circuit on or the lights on, then it's going to go on. This is a very important function, especially the electrical engineers will see this more in the circuit theory, or in the the 1001s, in the internet, in the deep learning theory. Also, this is some kind of important function. And what can we say about the limits here? The limit as x goes to 0 from the left of this function is 0, but the limit from the right as x goes to 0 from the right is equal to 1. As you see, they are not equal, and also we know that the limit doesn't exist as 0. Limit as x goes to 0 of this function doesn't exist. Shortly, you can also see this notation for this doesn't exist, DNE, which means does not exist. Okay. Another example is step functions, general step functions. Again, these are going to be very important in the integration. Like, for instance, we can have this function f of x equals this notation. This function means so the greatest integer smaller than x. So, for instance, you can think about f of 1.45. Then this function will give the greatest integer, which is smaller than this 1.45, is equal to 1, right? Because 1 is the greatest integer smaller than 1.45. Or you can also have, let's say, 0.3. Then this function gives 0. For negative numbers, if you have, let's say, minus 0.6, now we are going to think about the greatest integer, but less than this number. So that number is minus 1, okay? And when we sketch the graph of this function, it's going to look like a step function, a ladder. So it's going to be something like this. This is 0, this is 1. And then for numbers between 1 and 2, it's going to give 1. For numbers like 2 or bigger, but less than 3, it's going to give 2. For numbers between 0 and minus 1, it's going to give minus 1 until 0. Okay? Let me carry this somewhere else. Okay? So it's going to go like that. This will be, of course, minus 2. Okay? So this is a step function. And you can look at, for instance, the limits at the integers. Let's say the limit at 1 from the left. What happens from the left of 1? This function gives 0 from the left, right? The values are approaching to 0 from the left. But from the right of 1, the function, the right of 1, we are approaching to 1. So as you see, there is no limit at the integers. So this function has no limit at the integers. Integers are, remember, minus 3, minus 2, minus 1, 0, 1, 2, etc. Okay, all these numbers, which could be plus or minus, and this is another important kind of function, which again, as I said, will be maybe seen in the integration theory. And now the next thing I'm going to talk about is the properties of limits, or I should rather say the limit laws. So there are a bunch of laws which are very useful, and we are going to use these laws to calculate limits. So first of all, assume that C is some constant number. So it's just constant. It's always, let's say, 1 or always 2, always -4, whatever. And then we also know that the limits limit x goes to a of f is, let's say, L, and the limit of g as x goes to a is, let's say, m, where L and n are finite numbers exist. That means L, m, finite real numbers. So in this case, we have the following laws. 1. The limit as x goes to a of f plus x plus g of x is equal to the limit of f as x goes to a plus the limit of g as x goes to a, which is equal to L plus m. And then similarly, we can have subtraction of these limits. F minus g as x goes to a is going to be equal to the subtraction of the limits of limit of f and limit of g, which is equal to, of course, L minus m. And then we can have the limit of f, but some constant c, as we said earlier, it's a constant. This is equal to c times the limit of f as x goes to a. Well, of course, that's going to be c times L. And then we can also have product or quotient of limits. So if limit x goes to a of f times g, then we can calculate this limit just by multiplying the limits of f and g. So limit of f times limit of g as x goes to a each, which is equal to L times m. Again, similarly, we can have quotient of two functions, and then if you want to look at the limit as x goes to a, then we can take the quotient of the limits, which is going to give us the result, which is L over m. Here, of course, we don't want m to be 0, otherwise it's going to be undefined. And then there are some other laws. Let me write them. If we have the nth power of f, then we can use property 5, or property 4. We can multiply f n times by itself, then it's going to give us the nth power of the limit as x goes to. So that's going to be L to the n. The other thing is limits of constant functions like c is also c can be considered as a constant function, then the limit is simply c. And also, if we have the function x, just simple x, y equals x function, then if x goes to a, of course, the limit will be a, right? Because think about it. This is y equals x function. And then if x goes to a, then the limit will also go to a. Or think about the constant function here. It's constantly c. So when x goes to a, as you see, all of the values will be c anyway. And then another law is limit as x goes to a of x to the n is a to the n. Again, you can use property 6 and property 8. So by 6 and 8, first you can multiply limits of x n times, but they are equal to a, and then multiplying a n times by itself will give a to the n. Okay, here n is a positive integer. Okay, maybe I forgot to say, but here also n positive integer. Also, a similar rule is if we have the nth root of x, when x goes to a, this is going to go to nth root of a. Okay, but we want n positive even integers. So when we say positive integer here, we say 1, 2, 3, 4. But when we say positive even integer, we mean 2, 4, 6, 8, so on and so forth. Also, we all should assume that a is positive, because if a is not positive, then we can take the square root or even root of a negative number. So we need to have that a to be positive. Another rule is the nth root of some function is equal to nth root of the limit of the function. And if the limit of the function there is L, then we have nth root of L. And again, we want n to be even integer, positive integer. And also we want L to be positive. Otherwise, we can't take the, again, I mean, if n is even integer, here, if n is positive integer, then a must be positive. If n is not positive integer, then everything is fine. Here also, okay, this one is fine. So anyway, so we have this rule. Is there any other rule I want to say? Let me do some examples. For instance, limit of x goes to, let's say, 3 of 5x squared minus 6x plus 1. Then first we can write each limit separately. But remember, 1 is a constant function, so the limit there will be 1. And you can take that 5 outside, 6 outside, so maybe I should write them too. So the next step will be 5 times limit x goes to 3 of x squared, and then take that minus 6 out. X goes to 3, limit of x, and then limit of the constant function is that function, whatever constant that is, which is 1 in this case. For the others, we just put 3 for x, 3 squared times 5, and then minus 6 times 3. I'm applying the rules that I have written above. And then what do I have? 5 times 9 minus 18 plus 1. This is equal to 45. So 45 plus 1, 46 minus 18, that's equal to 28. Okay, so you can do many examples like that. So let me do one more. So let's say we have limit x goes to 1 of, let's say, square root of x minus 1 over, let's say, x cubed plus 2x. Then what's going to happen? I'm just going to write first the limit on the top and on the bottom. And I'm going to use the sixth property if I'm not wrong. And then I'm going to carry the limit inside the square root. Here I'm just going to write limit separately for x cubed and the other one. And then, you can go a few more steps like for the x and minus 1 and then taking the 2 out. But anyway, so we can eventually put 1 for x. And what are we going to get? We are going to get this square root of 0 over 1 plus 2. That's 0 over 3, which is 0. Okay, so of course, I just wanted to show how we use the laws, but we will just skip the middle steps. We will just put 1 for x as long as the functions are the functions that we can apply these rules. And then we are just going to find the result. There is another property. This is called, actually what I did here is kind of using this property, but I actually used laws, but you may skip those laws if necessary, if f is a polynomial or a rational function. And also we want a to be in the domain. So this is actually a special case, as you see. First we cannot have always f to be a polynomial or a rational function. That's not always the case, but if this is the case, and again, as I said, a doesn't have to be in the domain, but if it is in the domain, then the direct substitution property is this. We directly substitute a for f, and then we get this. Okay. Well, this is something about the continuity of polynomials and rational functions, but we are going to come to that later. How about some other examples? So these are more interesting examples. So let's say find limit x goes to 2 of x squared minus 4 over x minus 2. Now, if you directly put 2 here, you are going to have 2 squared minus 4 over 2 minus 2, which is 0 over 0. So, well, this is not an answer. So we can still do something more here. If you have a 0 over 0, then that means there is something you can do. Okay, if at first you find a 0 over 0, then there is something done. There is a trick, or let's say something you can do and calculate the limit. So you just need to know these tricks. So in this case, what can we do? Well, what we can do is, if I write this thing again, I can factor x squared minus 4. So x minus 2 times x plus 2, because I can factor it like that. And then, as you see, I can simplify x minus 2 and okay, where did my 2 go? Okay, oops. So okay, so I can actually simplify this x minus 2 and this x minus 2. Then what will happen? There will be a 1 here left, and then there will be a 1 left here. So after this simplification, this will simplify to x plus 2 over 1. And then dividing anything by 1 is that thing. So just put 2 for x, 2 plus 2, that's equal to 4. Okay. By the way, I have used this property here. If you have a squared minus b squared, you can always factor it like a minus b times a plus b. This is what I did here. Okay, so I used this actually. X here, a is x, b is 2 in my case. So I wrote x minus 2 times x plus 2 instead of x squared minus 4. And then, as you see, I have found a number. Now, if you sketch the graph of this function, you are going to see something like this. This is going to look like x plus 2 line. So, but there is going to be a hole at 2. Okay, and when x goes to 2, the function goes to 4. But this function is x squared minus 4 over x minus 2 function. Okay, if the it's almost like x plus 2 line, but as you see at x equals 2, it's undefined. So we just show it with a hole in the graph for the line graph of x plus 2. Another example is this one. Let's say we have x goes to 1 of square root of x plus 8 minus 3 over x minus 1, let's say. So if we put 1 here, we are going to have 1 plus 8 square root of 1 plus 8 minus 3 over 1 minus 1. But that's equal to square root of 9 minus 3 over 0, or square root of 9 is 3, 3 minus 3 over 0, or 0 over 0. Again, be careful here. We have a 0 over 0. So that means there is something we can do here. Now, in this case, there is a different trick. So in this case, we are going to use that trick in the previous example backwards. Like, what am I saying here? So I'm gonna multiply top and bottom by the conjugate of the expression on the top, both top and bottom. So this is called conjugate of square root of x plus 8 minus 3. So square root of x plus 8 minus 3 is and square root of x plus 8 plus 3, these are conjugates of each other. And when you see a square root stuff like this, which gives a 0 over 0 when you take the limit, the trick is multiply both top and bottom by the conjugate. So what's going to happen? So what I'm saying here is I'm actually doing this, a minus b times a plus b. Remember the previous trick, it's going to give me a squared minus b squared. So I'm going to get a squared minus b squared. So that means I'm going to have square root of x plus 8 minus 3 squared. On the bottom, I just rewrite it. I don't do anything. And then what's going to happen after this? It's going to be x plus 8 square of, square of square root, just the same thing again, x plus 8. You take the square root and then you take square. They are inverse functions of each other, so you just end up with x plus 8. But what is square of 3? It's 9. And then if I divide this by x minus 1 times square root of x plus 8 plus 3, the top is equal to x minus 1, right? Plus 8 minus 9, that's x minus 1. So again, simplification, this is 1, this is also 1. So after the simplification, I have limit of x goes to 1 over that conjugate term, and then now put 1 for x. 1 over square root of 1 plus 8 plus 3, which is square root of 9 plus 3, but that's 1 over 3 plus 3, which is 1 over 6. As you see, now you have obtained a number. Okay. Another example, and this is the last example for this. Let's say evaluate limit h goes to 0 of 2 plus h squared minus 4 over h. Now, if you put 0 here, what's going to happen? You are going to have 2 plus 0 squared minus 4 over 0. This is 2 squared, so 4 minus 4 over 0, 0 over 0. Okay. Again a 0 over 0. Well, what can we do? Well, in this case, just expand 2 plus h squared. So let's calculate it separately with a different color. So 2 plus h squared is 2 plus h times 2 plus h. This is equal to 2 times 2, 4. 2 times h, 2h. H times 2, 2h. H times h, h squared. So sum and write that up. That's going to be 4 plus 2h plus 2h, 4h. They are like terms. And then plus h squared. Well, we still have a minus 4 over h. Now, you see 4 and minus 4 cancels. So this number here and this number here cancels. 0, 0 this time. So what have we left? We have 4h plus h squared on the top. and h on the bottom. Now put 0 for h. Again, you are going to have 4 times 0 plus 0 squared over 0, which is 0 over 0. Well, oh, okay. Still have 0 over 0. Well, then we need to do something here. What is that? We have to factor the top actually. There is a common factor h there. H times 4 plus h all over h. And then simplify the fours. Simplify the h's. So they will be 1 and 1. And this is equal to 4 plus h. And let h go to 0. That's going to be 4 plus 0, 4. As you see, we have obtained a result.